Okay, class, welcome to lecture 22. Today we're talking about the inverse of a function. So the idea is this. Whoops, first I need a marker. Okay, so given a function, you've seen the word inverse no doubt before, in maybe other classes and other contexts. So given a function from a set to another set, you want to think about the following couple of questions. Is there a function going backwards, meaning it goes from B to A, and it's defined by just doing the opposite of F. So whatever F does, it sends a bunch of stuff to B. Can I send everything back in the opposite way? Which is a cool concept to think about. Lots of functions you can think of as processes. So this is asking, like, are all processes reversible? Can you reverse a process in general to go back where it came from? No. And we'll see that you can't do that with functions either. That leads to the next question. So when does such a function exist? Just for like a silly example, if I cook a chicken, I don't know, what do people eat? I guess chicken. If I cook a chicken, there's no way to undo that process. It's just stuck. And then whenever you learn something new, you want to learn about what properties it has. And by it, I mean the function going backwards, if it exists. So when does it exist is the first question I have to answer before that. Okay, so let's just look at mini examples first. That's always a good place to start when you're learning something new. So I think that whenever you're doing mini examples, the best way to do it is with these like little pictures here. So let's have this be our two sets, A and B. So this would be A, this would be B. So A has X, Y, and Z, B has A, B, and C. And then remember, we can just define a function by saying where all the elements go, as long as we obey the rules of a function, then this tells us the function. Okay, so that's a function. So can I make it go backwards? Can I make a function going from B to A that just does what the opposite of F? Yeah, so I can just use my picture. So what does it mean to do the opposite? Well, where did X go? It went to A, so I'm going to send A back to X. Y went to C, so I'm going to send C back to Y. And B went to Z, or sorry, Z went to B, so I'm going to send B back to Z. So this is what I mean by doing the opposite of what F does. It just sort of reverses F. It goes backwards. So this, I didn't name the function yet, but I will soon enough. Okay, so this is, the idea here is it's possible to do F backwards. So you can also sort of think of it as undoing F. If I hit Control Z, I think that's undo, then I go back. That's sort of what this function is doing. So that's a situation where such a function can be reversed. The process can be reversed. So let's try to think about when it would be impossible to reverse a function. So here's a situation. So if I send A to X and I also send B to X, then I send C to Y. So it's a little bit different than last time. Then I can try to do the reverse, and we'll see what goes wrong. So So if reversing creates the following. So I'm supposed to send X and Y back to A, B, and C according to just doing this in reverse. So X has to go to A, but it also has to go to B, and Y has to go to C. But what's wrong with this picture? This is no longer a function. So reversing this process creates something that's not a function. That's not what we want. We want a function that goes backwards. So what this is saying is that this guy does not really have a reversible function that goes backwards. So here it does not exist. And we can see the issue is with this element X. It's got two things going into it. So when I try to reverse the process, where do I send X? Because I got to send it to A and B, but a function never sends one element to two different places. So that's the problem with that. And then there are other issues that can be created if you make other examples. So I'll leave you to try to create other issues that show up. But I think that is enough for us, enough mini examples to jump to the definition of what we're trying to talk about here. Okay, so given a function from A to B, we get this other thing, the function called f to the negative 1, which is read as f inverse. Now that negative 1 is sort of hinting at something, but it doesn't mean like what the negative 1 power does for a number. Okay, so that's why we read it as f inverse, not f to the negative 1. So the function called f inverse that goes back from B to A, defined by, so to define a function, I have to say where elements go from the domain. So where am I going to send B? Well, I'm going to send B to A, but what is this A? It's the A that got sent to B in the first place by F. So this is how I'm defining this function. I'm just sending every single B back to the A that got sent to it in the first place by F. That's the definition of this function. But it doesn't always exist, so I do have to have a little caveat to this definition. I have to actually say if it exists. If it exists, it doesn't have to exist as we've just seen. It's called the inverse of F. Now, the word the is very important because in the lecture problems, we're going to talk about how inverses are unique. So if a function does have an inverse, then it only has one inverse. There's no other way to go backwards to undo the function. Okay, so we're sort of annoyed right now because we have to worry about like, oh, it doesn't always exist. So it's sort of stuck in limbo. We have this definition of taking a function and then creating this other function that goes backwards, but doesn't always exist. So it's kind of annoying. So before we talk about inverses more, let's just establish when the inverse actually exists so that we can always work in the situation where it exists. So let's establish when f inverse exists. Luckily, it's not so bad and it's hinted at by the example. And I'm going to even call it a theorem because it's a big deal. So let f go from A to B, be a function. So the idea, let me just scroll back up to the pictures real quick. It's wonderful. Why is this one invertible, but this one is not? Well, it's really because this function here is bijective. Every guy goes to one guy. There's no overlap. And everything in the codomain gets covered. So it's injective and surjective. That's really what it takes. If you have that, then when you want to send things back, you know exactly where it should go. It should go there. It should go there. You don't have any of these overlap issues. So that's what it takes. It takes f being bijective. So that's what we're going to write here. So then f inverse exists. We're establishing a situation where it exists, and this is the only time it exists. So what we're going to do is do an if and only if proof. This is the only way that an inverse will exist. If something else happens, it's got to be equivalent to f being bijective. That's what you're establishing when you're establishing an if and only if. You're saying that these two things are saying the exact same thing. And so the only way that the inverse can exist is if f is bijective. Of course, there are other ways to say f is bijective. You could say f is surjective and injective. That's also the same. But the point is, f being bijective has to happen somehow for f to be invertible, to have an inverse. Okay, so let's do the proof. Because it is a if and only if, I have to prove both directions. So first I have to let f inverse exist, and then I have to show f is a bijection, or f is bijective. As a result, that proves one direction of the if and only if. Okay, so to show something as bijective, that actually has two proofs, so it's two proofs inside of this proof already. So we got to really show f is injective and surjective. Luckily, we've been doing those a bunch now, so hopefully they're not so bad. Okay, so first we'll show f is injective. And how does that work? I have to let two elements be in the domain of f, and so f is going from A to B, so the domain is A. So I let two things be in A, and I assume that they get sent to the same place. Then I got to show that they came from the place secretly all along. It's a big secret, don't tell anybody. So let's do that. Okay, and all we know is that the inverse exists. So we have to use that somehow in our proof from getting from here to here. And I think I know how. So since f of A1, well, when I plug something from A in, that means the result is in B because A goes to B. So I'm just going to name what it goes to just so I can use it for a second. But that equals f of A2 as well. So I can really sneak another equal sign in there. What does this mean? Well, what does it mean for the inverse to exist? It means that it does this. If I plug in an element of B, it goes to the A that got sent to it in the first place. So since f inverse exists, that means that f inverse of B has to be A1, and f inverse of B has to be A2. But f inverse exists, and I should also mention it existing, I'm implying that it's already a function. So since it's a function, every element can only go to one thing. So B cannot go to two different things. It can go to only one thing. So that means that the two things that it's going to must be the same. Otherwise, f inverse wouldn't be a function. And so I've proven what I wanted to. I've shown that A1 equals A2, f is injective. Okay, so now let's show f is surjective. To show a function is surjective, we let something be in the codomain of that function, and we find something that maps to it. This shows everything in B gets hit by the function f. Okay, so all we know right now is that we have an element of B and that f inverse exists, and we know how f inverse works. So since f inverse exists and it's a function, functions have to send every element somewhere. So that means f inverse of B is a defined thing, and it's some element in A. I don't know which one it is, but it's something. Because f inverse is a function, it has to send B somewhere. So it's got to be something in A. I don't know what it is. But this is the A I want. This is the A. I even called it the same thing, little a. So then by definition of what the inverse is, if f inverse of B equals A, that means that A got sent to B in the first place. And this shows f is surjective because I was able to find an element that maps to little b. Okay, so f is bijective. I did both proofs. Now the backwards direction, I have to assume f is bijective, and I have to show f inverse exists. But what this really means is I'm showing that the process of sending a b back to A is actually a function. So no weird issues happen where I send one element to two different things, or I don't send an element anywhere. That would also be bad. Okay, so I have to show that f inverse is really a function. And so what that means is that I have to say where all the b's go. So we need to say what f inverse of B is for every b in B, and ensure that f inverse of B is just one thing for every b that you pick. What am I doing? Meaning I don't send a single b to two different elements of A. Okay, so I have to use that f is bijective because it was assumed, so it must come into play. Otherwise, I wouldn't assume it. So let's use that. So let B be in B. I'm trying to say what f inverse of B is. I'm trying to send this somewhere. Well, I have an element of B. Since f is surjective because it's bijective, that must mean that there's an A such that f of A equals B. That's what it means for a function to already be given to you as surjective. If you have an element of the codomain, you can find an element of the domain to map to it. So this gives me something to send B to using the inverse. So this allows me to send B to an element of A. So this ensures every element of B is assigned to an element of A. That's the first part of being a function. The second part is that every element of B is assigned to a unique element of A. It doesn't go to two different places. That's where injectivity will come in. So since f is injective, what can I do next? Well, if the inverse happened to send B to two different A's, I can do something because f is injective. Well, if this happens, that means that the function f must have sent a1 to b, and it must have also sent a2 to b, because b is going back to a1 and a2 at the same time. But then they both go to b, so they're equal. And now I can use that f as injective. So really, I shouldn't have said this up here. Let me cross that out. I didn't use that f was injective yet. Now I'm using it. So since f is injective, because I'm in a situation where two elements are mapped to the same place, I can conclude that the two elements are actually the same. And so this ensures that if the inverse process sent my element B to two different places, it turns out it actually sent it to one place. They're the same thing. So this ensures that F inverse sends B and B to exactly one element, A and A. Because if it sent it to two different ones, well, secretly they would be the same all along. And so that's why F inverse is a function. Okay, so that's the end of the proof. So we've done both directions, so we're all good. So let's just think of a very small example to bring ourselves back down to reality from all the abstraction. So here's just a regular old function, good old-fashioned function from pre-calculus or something. I don't know when you learned this, 2nd grade? It's been a while. So this guy has an inverse because it's bijective. And you can prove it's bijective if you want for fun. It's like we did in the last lecture. I'm not going to do it later. Now we're going to figure out how to determine the actual inverse. Right now, we've just said we know it exists. Now, you're probably familiar with this little process in pre-calculus. You do this trick. You say, okay, pretend that this is y. Now, switch x and y. Now, resolve for y. That's the inverse. And then you're just supposed to say, yep, I definitely know why that's the inverse in pre-calc. I definitely don't ask me why, but I can just do it and it works. And all my pre-calc students can do this, but they don't know why that's the inverse. So it's like this big magical mystery. But yes, this will actually tell you how to create the inverse. That'll take you back. So if I plug 10 in here or something, then whatever that goes to, if I plug that back in here, it'll go back to 10. Okay, so we got to figure that out. So why does that work? That's more important than knowing that it works. All right, well, we have to establish some more theorems before we can think about that, but that is one thing to think about. So here is another way to think about the inverse as sort of an undoing process. So suppose you already know that these are functions. So that means we already know f is bijective and it has an inverse that exists. Then the other way to think about the inverse is that it undoes the function, meaning that if I plug an element of A into F and then I plug that result into the inverse, it's just going to take me back to A because I'm just sending it over to B and then I'm sending it right back to where it came from. Similarly, if I first plug in B to the inverse, that's going to take me over to the set A. And then if I do F, I'll just send that right back to B where it came from. You can think of this as sort of like they cancel each other out. That's one way to think about it. This happens for any A in A and for any B in B. The inverse and the function undo each other. They cancel each other out. A couple different ways to think about it. Okay, so let's prove this one. Let A be an A. So I want to show that this happens. So how do I do that? Well, it's sort of just writing everything out in a sort of annoying way. Well, since A is an A, f of A is some element of B. So I don't know, I'll call it Y because I don't want to use the letter B because I'm using that for later. So that's some element of A, or sorry, of B, because I sent it using F to B. I don't know where I sent it, so I'm just going to call it Y. Then, just by the definition of the inverse, that means that the inverse function will send that Y back to A. That's just the definition of what the inverse does. So now I have both things. I can figure this guy out on the left. So what is F inverse of f of A? Well, f of A, that is just Y, and then f inverse of Y takes me back to A. So we've proven the first part. I'll leave it to you to do the second part. It works the same, but you start with a B and B instead of an A and A. So try that yourself. But it works just the same. Okay, that's because this lecture is going to be a long one, so we got to save some time. So this theorem basically just says that composing, that's really what we're doing up there, the inverse function with the function in either order is the same as doing nothing. And I'm putting this in quotes because you might remember this from the lecture problems. What does it really mean to do nothing? Well, in pictures, we can think about it like this. If I have A and B, and I take my element here and I send it over somewhere here, then I just send it back with F and F inverse. Well, I do nothing because I just sent X to X. And if I start on the right, I do nothing because I just send Y to Y by going this way and then this way versus this way and then this way. So that's the idea in which it does nothing. But in fancier terms, which we figured out in the lecture problems, we can restate this. So in other words, if I sub s, this is called the identity function, on S, so you can just change S to whatever set you want, meaning it's defined by doing nothing. It takes X to X, no matter what X you start with. If that's just a way to say do nothing in a fancy term, then I can create this theorem to say what I just said in a fancy theorem way. So here it is. Let F go from A to B, and F inverse go from B to A, be its inverse. Then we have two nice facts. So we got to remember how composition works. It's a bit tricky. I write the first one on the right. So if I write F inverse compose F like this, I should think about where is this going from and to. Well, this is starting from B because F inverse starts at B. Then it's going to A, and then F is going back to B. So that's that. But more importantly, that composition is exactly equal to doing nothing on the set B. And similarly, if I go in the other order, so I do F first, that means I go from A to A, then that function, that composition, is exactly equal to doing nothing on the set A. So it's just a restatement of what I said before in a very fancy way. And in fact, the proof just is the same as the proof of the other theorem, because, so I'm not going to do it. I'll leave it to you to write it up formally if you'd like. It comes from just these facts that we just proved. Let me write them in the same order though. It just comes from the fact that this happens. For any B and B. And that is exactly just I B of B. What does that go to? Well, it does nothing. It sends it to B. And that this is the same as I A equals A. So that's what's going on. We could also draw this in one other nice picture. These pictures are always nice. There's little diagrams with arrows between little blobs. They're very helpful for visualizing what's going on. So the idea is I could go from A to A by doing nothing. That's what this guy is. Or I could get there in a very roundabout way. I can use my function f. That'll take me to some element of B. But since it has an inverse, I can just go right back using the inverse. And this is saying that both paths are the same. And in the other picture, it's just flipped around. And it's just saying that if I start with an element of B, I can do nothing, I can send it to itself, or I can get there in a very complicated way by first using the function f, and then going back. Actually, sorry, one of these is wrong. Then I can use f inverse. Which one is wrong? This one, because I'm going from B to A first, this one should be f inverse. Then I go back using f. So just the opposite of this one. Okay, just another way to visualize things. And lastly, I really want you to think about it, the inverse, as sort of like this too. So we can also think of, I guess I shouldn't say so, it's a separate thing. We can also think of inverses as sort of negatives in the following way. So maybe I'll make a little chart. People love charts. So we got our numbers and we got our functions. So to stick two numbers together, I could use plus. You can plus them together. And I can think of that as being similar to sticking functions together with a composition symbol. So that's sort of like my operation. And then there's this do nothing number corresponding to plus, which is called 0. Looks sort of like composition, but it's the number 0. And for functions, that the do nothing set, the do nothing function is the identity function on the set. And then to like undo something for numbers, it's the negative. And for functions, it's the inverse function. And they all work sort of the same, right? Because a plus negative a gets you to the do nothing, and f compose, f inverse gets you to the do nothing function. You could also think of the other operation for numbers that you're familiar with, which is multiplication. And this one is a bit more hinty at the notation we're using. So if I, instead of using plus, I use times, then the do nothing number is 1. And how do I take a and undo it to make it go back to the do nothing number? I have to multiply by 1 over a. But what do people call 1 over a? They call it a to the negative 1. That's where this notation comes from. So we reuse the same notation for two different things, even though it can be confusing, especially in pre-calculus, because this actually happens a lot. Okay, you will not believe how many times I have people try to find the inverse, and all they do is flip it over because they see this thing. Okay, so anyway, yeah, you should think of composition. You should compare it to other operations between numbers, and then you should think about what the thing that does nothing is for numbers. Then how do you undo the operation? You can also compare this to, I can't help myself, this wasn't even in the lecture. So what about like sets? So I could stick sets together with union. What's my do nothing element there, or my do nothing set? Well, the empty set, because if I union a set with the empty set, it doesn't do anything. So that's why it's the do nothing set. I guess I didn't write that for over here, but a plus 0 is the do nothing number because when I add it, it stays the same. If I compose the identity, it doesn't do anything. But anyway, so the empty set plays the same role. So how do you undo that? I'll leave that to you to think about. Oops. Okay, moving on. So using this, we can actually understand how inverses work for those old problems. So let's find the inverse of f from R to R defined by f of x equals 2x plus 7. So in pre-calc, they tell you to make it be y equals 2x plus 7, switch x and y, then resolve for y. So let's figure out why that actually works. So we know that the inverse has this property. If I plug in a y value to it, and then I do f of it, it should take me back to y. That's the definition, or that's one of the results we proved. But we proved it in general. So now we're just going to use it here. So what's f of x? It's 2x plus 7, so I'll just plug this thing into that function. So 2 times f inverse of y plus 7 equals y. So now I can figure out what f inverse of y should be to make y pop out, to undo my function by solving for it here. So I just subtract the 7 and divide by the 2. And that is exactly why that trick works. But for some reason in pre-calc, we teach it differently. We just say like, oh, just, I don't know why, but magic, you're just gonna switch x and y, and then you're gonna resolve for y. Oops, there should be a 7 there. And magic, that'll work. And then that's the function. Here, I guess the reason they do it is because in pre-calc, you cannot handle the fact that you could use a different variable. It has to be x or else you'll die in that class. Here, we're more mature, so we say, you could just keep it as a y. The point is, it goes backwards this way. So it's taking your previous outputs and sending them back. So I guess you like to call outputs y in that class. So that's why we use y here. Okay, so anyway, that's why that works. So this defines f inverse going back. Okay, it's always good to re-understand old things from a new perspective. Okay, so let's see. One more big property. So we answered when do inverses exist? How do you find them sometimes? And now we'll think of properties of inverses. So this is a cool one. How do inverses combine with composition? So now we're going to have two functions that are composable because they have domain and codomain matching for one and the other. So they got to be bijections. That way we can talk about inverses for both of them. That'll come in handy in a second. Okay, so they exist. The inverses exist. Well, then we've already shown last time, or maybe 2 times ago, I'm lost, that if I compose two bijections, it's a bijection. So I'm not going to prove that because we proved that before. Now I'm calling them bijections instead of saying they are bijective, but that's the same. Okay, so this is a bijection. So we know bijections always mean that the inverse exists. So that means that this guy exists. And I guess I might as well say what it goes from and to. Well, where does G compose F go from and to? Well, it starts at A and goes to C, so that means that the inverse of that should go from C back to A. Okay. And most importantly and most interestingly, the inverse of this composition is equal to doing the composition of the inverses in reverse order. So that's the really weird part. So you might say like, oh, I would have thought, so this will just be sort of scratch work. Why not this? Well, this guy doesn't actually make sense because this is saying first do F inverse, which goes from B back to A, then do G inverse, which goes from C back to B. So I can't go in that order because I can't go from B to A. How do I continue it? Because the next one has to go from C to B. So I can't do them in that order. It has to be the other order. Because if I do G inverse first, I can go from C to B. Then I can go from B to A at the F inverse. So this one makes sense. This one doesn't, first of all. Okay. So now let's prove it. All right, so we got all this information. F goes from there to there. G goes from there to there. So they're composable. They're both bijective. That's great. We already proved that the composite of bijective functions is therefore bijective. So we're not going to reprove that. But what's new from today is because it's bijective, the inverse exists already. It must exist. We're just trying to figure out what it is. Okay. So now let's show this. So to show two functions are equal just means that you have to show that they do the same thing when you plug in the same elements. So, and you have to do this arbitrarily. So that means I have to let something be in the domain. So the domain of both of these is C, right? Because it goes from C to A. So let something be in the domain and show that when I plug it into either one, the result is the same. that shows that they are the same function. They do the same thing to the same elements. Okay. Okay, so how do we go about this? Well, the only information I have to start with is that C is an element of C. But I got all this other stuff that I've assumed. I know that both of these guys are bijective. Well, I can immediately use that G is bijective. Since G is bijective, I'm really using the surjective part. But I'll just say the whole thing. That means that because I found something in the codomain, there exists something in the domain that maps to it. Really, where the bijective part is coming in is just to tell us that G is invertible, but here we're just using the surjective part. We are secretly using the injective part to say something else, but I'm not going to, there's too much going on already, so we'll ignore that for now. Okay, the point is that I can find a B that maps to C because G is surjective. And then by definition of the inverse, that means that G inverse of C is B because it does the opposite of G. Now, since I have an element in B, and this guy is bijective, I can just do the same thing again. I have something in the codomain because it's bijective and therefore surjective. There's got to be this other element in A that I can plug in to get to B. And because it's invertible, the inverse is defined in this way. So now I have the information I need to calculate one of these things. Because how is composition defined? Well, it's just defined. What is this thing really? It's just saying do G inverse of C first, then plug all that into F inverse. That's what this really is defined to be. Now I know what these things are. G inverse of C, that's just B. F inverse of B, that's just A. So here, C goes to this A that I created. So what I want to do is show that this thing also gives me A. And here's why it does. This thing is literally the inverse of G compose F. So it just does the opposite of whatever G compose F does. So let's see what G compose F does to this same A. So this is the same A as the one that exists because of all this other stuff. Well, by definition, that's just this. So plugging it into F, then plugging it into G. Okay, but what is F of A? We already know what that is. It's B. And what's G of B? We already know what that is. It's C. So by the definition of the inverse, because G compose F sends A to C, the inverse of it must send C back to A. But that's exactly what this other thing was. So they send the same element to the same place, thus they are the same. So the whole point is that if you want to invert a composition, all you have to do is invert each function independently and then compose them in the reverse order. That's what this is really saying. Okay, so in the lecture problems, you're going to do an alternate proof of this in a more fancy way after some other stuff, but that's it for the lecture. Okay, see you next time.